Now we have the second class of the short course by Guilherme Raposo, who will tell us about compact objects and how to model them.
Okay, thank you. Can you hear me well? Great. So, by the way, Portugal is playing now, so let me know how the game is going. And so, yeah, today we're going to go to the second part of the course that we started yesterday. And so yesterday, as I mentioned, it was a very sort of basic, very light introduction to compact objects modeled by fluids. And yeah, the idea today is to sort of extend a bit that to more interesting forms of matter. And specifically because we want to study what I called yesterday exotic compact objects. And so, exactly, this is sort of what we've seen yesterday. We sort of saw how can we model, let's say, a star or a compact object with some liquid, with some fluid. And we saw some different types of equations of state, particularly polytropics and equations of state with constant sound speeds. And our entire motivation for that I sort of mentioned in the last parts of the lecture, if you recall, is basically to model these types of compact objects that are not neutron stars, they are not black holes, they are something else that we currently don't know. These are the exotic compact objects that we've, well, have learned a lot about here today and yesterday actually. And actually I'm going to go a bit beyond the objects that you probably have heard more here, for example the ones that Carolina talked today. I'm not going to talk about boson stars because I know that, well, there were other people talking about that, so I'm going to focus on other types of matter. But let's just go to, well, for some more basic approach at the start. If we have these exotic compact objects, which I mean the short form is echoes as represented there, we should have sort of a wish list of things that we want them to satisfy, because if they are supposed to represent a possible alternative to a black hole in this sense, they should have at least less problems. So if they are something that can form in nature, let's say, you want a couple of things. First, that they are, well, by construction, horizonless and singularity free. Otherwise, at that point, they already have the same problems as black holes. And you want them to be at least sufficiently stable. So if you take this compact object that is possible in our universe and you start poking the compact object, you don't want him to collapse immediately or to dissipate. You want them to, well, to at least play some real role in astrophysics in the universe. But more than that, you actually want this to be formed by, well, some formation mechanism that you can understand. Otherwise, it does not make really much sense. And this actually is related to what Carolina talked about before, about boson stars. Boson stars are actually the only sort of these models of compact objects that have, well, at least a well-understood way that they can be formed. Other types of compact objects are much more complicated. Well, exotic compact objects. Neutron stars, you know how they are formed. And so, you also want something else. You want at least to have some well-understood dynamics. So, if you have this model of your lovely exotic compact object, but the theory or the way that you model them does not allow you to explore anything about dynamics. So if you take two of these objects and you don't know how they can merge, if you don't know how a single object evolve, you don't know how the equation can work around these compact objects, well, then it's not a very interesting model to do science. So these are sort of the four big things that you want in order to have, let's say, a good exotic compact object. But these are very difficult things actually to satisfy. And as I've sort of implied before, we have a zoo of these compact objects, but very few, or basically only boson stars, satisfy most of these conditions here. But this does not mean that we should not explore other options. They are still interesting, at least if you want to do some, for example, comparisons with the black hole and understand some phenomenology. But okay, now we have sort of two approaches to do this. You can pick one of these compact objects that you like, and there are, well, a lot of options if you want, and study it. Or there are some other, depending on the type of work that you want to do sort of a parameterized eco model where you sort of have an object with some surface that is a bit outside the horizon, and you parameterize that surface by, well, some parameters, and this will sort of give you a toy model for these compact objects. And depending on the type of work that you want to do, you can choose either of these approaches. Okay, and so, as I've mentioned, we have a lot of these compact objects, so it's good to have sort of a compass to understand how to construct them. And this goes back to what we had yesterday. I had this figure here with the Buchdahl bound. If you don't recall, Buchdahl bound sort of says what is the maximum compactness that you really can have for a fluid compact object, and there's some set of assumptions, right? And the big thing here is that even if this is sort of for unrealistic fluids, it still does not go towards the black hole limit. Well, it was shown that if you start to break some of these assumptions that we have here, you can in fact go toward this black hole limit and construct sort of exotic compact objects. So for example, at each assumption that you start to break down, you are sort of hiding under it a new type of compact object. For example, if you consider exotic matter, you can perhaps go towards form these ultra compact objects. If you consider other fields, also does not necessarily need to satisfy this bound. And yeah, exactly all these that are written here. So you get the idea. And so now we can sort of use this compass to try to understand how we can construct these compact objects. And I'm going to start with the, well, the simplest cases. So this is, well, one of the most vanilla cases that you can do, which is the wormhole. Basically imagine that you have outside in vacuum the Schwarzschild solution, and you just say that, well, at some point of the space-time there's a surface, and of course always the question is what's going on inside of that surface. What is the state of matter? What is the solution there? This is always the question that you want to answer. In this very simple vanilla case, you just, well, you say, well, let's match this with another Schwarzschild solution, glue them, and this becomes the throat of the wormhole, as you probably have heard in your GR courses. This is, well, perhaps one of the most simple. Then there is another very simple case, which is sort of the Gravastar case that I'm just going to mention here briefly, which is sort of very similar, but instead of matching with the Schwarzschild solution inside, you sort of match with the de Sitter space-time. And this, well, of course, like the last case, this sort of sets some boundary conditions at the surface. But in this case, basically the object is supported by this de Sitter pressure that is inside. Okay, but the thing that I want to highlight here is that in these two cases that I've just mentioned, this is very forced, right? I mean, you can understand that I'm just saying that I'm gluing two solutions. I'm not saying anything about this can be formed. I'm not saying anything about dynamics. And of course, this does not seem the right way to do if you want to do, well, imagine dynamical simulations or things like that, because you don't really have a way to, well, do more than this that I've just said. Even the stability studies are very complicated. So we need to go a bit beyond this. And I'm going to focus on one case that was not discussed here, which are anisotropic stars. And this, as the name says, is exactly obtained by removing this isotropy assumption of this Buchdahl theorem or this Buchdahl limit. And we'll see exactly how we can construct these objects. So this is a long story now. This sort of the first discussion of anisotropy in the context of stars actually was in the beginning of the 20th century, in the context of some spheroidal stars. But again, I quote here, recently in 1974, so before I was born, this is when the interest started again with this work by Bowers and Young that was studying basically the the structure of anisotropy, I think in quark stars, but I don't really remember exactly. Maybe I'm wrong. And well, after that, there were a lot of these works that started to have interest in understanding what can be the structure of stars that have these anisotropic pressures inside. And well, until very recently, this was an ongoing work, and still is. However, I should note that anisotropic stars have some possible problems, and I think the best way to see that is to start by looking at the stress energy tensor of this type of matter. This is very similar to the stress energy tensor of the fluid. Sorry, here the notation is not the same as I said in the last lesson. So the first term, again, is the energy density, but here is a mu. The second term in the matrix is the radial pressure, and the two other terms are the tangential pressures. So again, for these anisotropic stars in spherical symmetry, which is the case that I'm considering, these last two need to be the same, otherwise it's not spherically symmetric. And okay, if you put this in Einstein's equations plus the stress energy tensor conservation, this will lead you to what we now call the anisotropic Tolman-Oppenheimer-Volkov equations. And these are actually very simple equations, similar to the ones that we've studied yesterday. And the funny thing is that the two equations are exactly the same, and the only modification appears in the equation that tells you how the pressure behaves, where you introduce this last term, which is basically the correction due to the anisotropy. The term radial pressure minus tangential pressure is what we call anisotropy. When these two things are the same, the object is isotropic. And okay, if you look at this equation, you already see that there's something that's going wrong here. Because, well, the pressure can be finite at the center, but this last term that we have here goes with 1 over r. So at the center, this term blows up. So what this tells you is that the solution that you have is singular unless you have some way to make this anisotropy vanish at the center. And turns out that this is not very easy to do. Whatever anisotropic mechanism that you are thinking that you have must make this pressure to be isotropic at the center of the star. And so Bowers and Young, when they started to work on this, they postulated this sort of equation of state that said that the anisotropy, the left-hand side term, is equal or proportional, let's say, to the GRR component of the metric, well, some functions that are not important here, and the radial coordinate squared. And this basically makes and forces that this term on the left-hand side is 0 when r is 0. And there are other sort of equations of state that follow the same principle. But I guess if you look at this equation of state, let's say, you can see already some problems. And problem 1, the first thing is that this is formulated for a static and spherical symmetric distribution of matter from this GRR and R coordinates that we have there. So if you are trying to generalize this to anything that is not spherical symmetric, it's not really trivial how you modify that equation, or if it makes sense. But there's more. So this equation of state is something that you just plug there. It does not, you are saying that you want this anisotropy to be motivated by something. Well, when you wrote this equation of state, you are not motivating by anything. You are just postulating something. So that's another problem, and it's something that you want to improve on. And then there's a third problem, that this sort of violates the principle of equivalence in its weak form, because, well, this is clearly something that is not covariant. Now, this third problem was sort of solved with the work that I've done with some collaborators a few years ago. And basically, the idea, so I lost the slide, does not matter. So the idea here is that you consider an equation of state that instead of being, well, something like this here, contains, well, says that the left-hand side is proportional to the covariant derivative of the pressure or the density, something like that. And that sort of solves this last problem. and you can obtain some solutions. Of course, it does not solve the other two problems, but well, it was a step forward. And so you can solve this TOV system similar to the way we did yesterday, or I showed how to do yesterday, and we obtain the solutions. And so these are sort of the highlights that you get when you construct these anisotropic stars. So here on the right figure, well, the only figure that's there, you have the mass radius diagram and the compactness radius diagram for different types of solutions. So this C sort of sets a scale on the strength of this anisotropy. And what you see is, well, first when C is 0, it's the isotropic fluid, and this corresponds to sort of this, well, this red line here. Well, it's red in my computer, but here it's something else. And what you see is that as you increase this C, the solutions become more massive and also become more compact. And so this is, well, something interesting when you are trying to study these sort of exotic compact objects. And another thing that you see is that as immediately as you turn on this parameter, any of these curves will go towards the compactness of a black hole for some given density. So these curves here are basically constructed by putting different values of central density, and points that are towards the left of this figure correspond to very dense solutions. And so these very dense solutions are approaching the compactness of a black hole. There's a second thing that is important here to mention, is the fact that these stars can exist in a wide range of masses. And this is, for example, a problem that we have for neutron stars. Well, for neutron stars it's not a problem, but for other compact objects, you cannot go to arbitrarily high masses. So imagine that you want to construct a model that is supposed to replace black holes. I'm not saying that's what I'm doing here, but imagine that you want to do that. You need to describe simultaneously with your model black holes that have stellar masses and black holes that have supermassive, well, that are supermassive black holes. And so this is one property of these solutions that could, in principle, do that. So there are more things that are interesting here. For example, the properties actually do not depend on the anisotropic scale, but more on the compactness, and you can see this from this figure on the right. So we have here basically the density, the pressure, the radial pressure, and the tangential pressures, and the curves are sort of grouped in pairs of two. And although the value of C is different in these two curves, what is similar between them is the compactness. So, for example, these two curves here have different values of C, but have the same compactness. For example, 0. I think is 35 exactly. And as you increase more this density and you approach the higher compactness and it goes towards this black hole limit, the solution actually becomes a constant density solution almost throughout the star, and also the radial pressure becomes almost constant until, well, it drops sharply at the radius. But the tangential pressure actually does not. It becomes very low, and then it has a very sharp jump and peak close to the radius. So this means that actually the dominant energy condition is violated for these stars close to the radius, for very compact stars, which is sort of a problem of these solutions, which is exactly what I just said. There's another good thing, because now that we allowed to, well, construct this covariant formalism, we could do at least numerical relativity simulations in 1+1, because we are still in spherical symmetry. And these allow, for example, to study the stability of the star, well, linearly, analytically, and with, well, comparing with what you get in your numerical simulations. And this is sort of what we saw. For example, on the right, we are just monitoring, for example, the central density. And you see that for unstable stars, which are the dashed lines, this blows up or goes down, while for stable stars, it sort of remains constant. And the thing that we sort of, well, were puzzled, and we still are not sure what happened there, is that when we compare the analytical and the numerical results, well, typically the stars numerically seem to be more stable than what I get analytically. For example, in this figure here on the right, of the peak shows where the maximum mass is, and it's the threshold for the stability. But apparently, according to our numerical simulations, the stars were stable even when they were supposed to be unstable linearly. But we are still not sure what was going on there. Okay, so this is sort of a very, in a nutshell, approach to the anisotropic stars. And again, I write here the three problems that I've just mentioned. And in fact, well, our equation of state solves the three, but this is clearly not the best way to approach the solutions for 1 and 2. However, recently, there were these two works, one by me and some collaborators, and another one that came out, well, I think on the day that I arrived here in Brazil, by Eric Poisson and I guess his student or collaborator. And they try to solve also some of these problems. And they are a bit different in approach. For example, in my case, I'm studying relativistic elasticity, and in the case of Eric Poisson, he was motivating his equation of state by a liquid crystal physics. But they have one thing in common that there was missing until now, is that they always start from a Lagrangian formalism. And this is, well, this seems to be a good step forward because, well, it's also what you sort of have for boson stars, right? You start from a Lagrangian formalism. And boson stars is a good example of how to model an exotic compact object. And so that's what I'm going to motivate now. I'm not going to talk about this one on the right, although I would love to. I did not have time to read that paper because there are 3 papers with about 40 pages each, so I was enjoying Brazil. And so I'll talk about mine because it's easier. So let's just introduce here the concept of relativistic elasticity. So classically, a rigid body, well, is an object for which is the distance between points are constant at any given instance in time. And now, if you think about this, this will immediately start to raise some red flags. Because all these concepts that I've just said here do not apply very well when you're talking about general relativity. These are frame-dependent concepts. So the conclusion is that there are no rigid bodies in relativity. And if you think, perhaps you have remembered your courses on relativity, and you think about the paradox of the barn and the pole, it really takes some time for the information on one end of the body to receive, well, it takes some time for one end of the body to receive the information about what happened in the other side of the body. There's no instantaneous propagation of information. And so, yeah, in fact, there are no rigid bodies. But the problem is even worse. And if you think about Herrnfest's paradox, so the paradox is as it follows, right? So consider a disk that is rotating, and you put some observers that are co-moving with the disk, and we are here outside, very far away. You start to spin the disk. From our point of view, the rulers of the observers that are moving with the disk will start to shorten, but the radius of the disk does not shorten because it's perpendicular to the velocity of the motion. So what this means is that the observers that are there will start to match a perimeter of the disk that is more than 2 pi r. And so, how does this solve? Well, basically means that the geometry of the disk is no longer flat and needs to be a deformed geometry. So, this means that there are no undeformable bodies also in relativity. I mean, in the sense, whenever you spin the disk deforms. And so this is why relativistic elasticity is important and actually is essential for general relativity. And so this goes back, well, a bit back in time by the works of Carter and Quintana. But two works that are actually very important, and I found it very interesting to read, is the work of Schmidt and Karlovin and Samuelson that arrived, well, in the beginning of this century. And I'm going to sketch here now sort of the gist of the theory. It's going to be a bit, well, cumbersome because these are people from the mathematical relativity community, and I'm going to do my best to try to translate the two languages, but I'm perhaps not the best expert on that, so please let me know if you don't understand something and I'll try my best to explain. How am I doing with time? Okay, perfect. Okay, so in order to construct basically an elastic body, you need three key ingredients. Three key ingredients. Well, the physical space-time, as the name says, is what you typically are used to, the space-time where your body are. Then you need something else. You need a reference space-time, which is sort of a three-Riemannian manifold, which represents the reference or rest state of your body. So I'll explain better later what it is. But it's related with the undeformed state of the body. And then you construct a projection map that will map these two spaces. And you construct it in some way that basically the level sets of this projection map are the world lines of these of the particles in the medium. And so let's go a bit more into detail about this last point here, this projection map, because the physical space-time there's not much to say. I think you are aware about what is a manifold, what is a metric. So this can be put in more concrete language by talking about coordinates. So this mapping, in some sense, is just a way of saying that how do the coordinates on the reference space, well, I said reference space-time, but again, there's no time there. It's just reference, I guess, space. How did these coordinates depend on the coordinates of your space-time? So you can think about it as, well, your, what I call here, the manifold S has some coordinates, I guess, hij, and these will depend on the coordinates x, y, z, and t from the space-time. So you can also think about it, if you prefer, as sort of a three scalar fields, which are these coordinates that will depend on the space-time coordinates. And so once these coordinates are assigned and you specify them, you basically can construct sort of basically this projection of the space-time metric that you have in your physical space-time in your reference space. And now let's think about a bit more on what this represents. So this projection of your space-time metric in the deformed space of the body will basically tell you sort of a definition of strain, because it will let you know what is the displacement that your particles in the medium suffered when they were deformed. And this gives you a definition for strain. Now, let's think a bit about why do we care about the reference space-time. Well, I'm going to ask you to think a bit about 2D, because otherwise we cannot visualize it, but let's consider that we have a surface that is sort of like half a sphere, half an hemisphere. And this is your object in the state that he wants to be in the laboratory, let's say. He wants to be half a sphere. And now I want to put this object traveling in a 2+1 Minkowski space-time. Well, if I did not know anything about the reference state, I would say that that looks very flat. But in fact, no, the object is sort of stretching, because its natural state is actually a half a sphere. So, in fact, this is stretching and deforming just because its natural state was not flat. So this is why the reference state is important. Now, I've said that, but in most cases that I'm going to talk here, either the reference state won't be important or it will be flat. but it's good to have it in mind. So typically, the way that you do it is you write a Lagrangian that is, well, depends on the coordinates or the fields that I've just mentioned before of your reference manifold, let's say. That will depend again on the coordinates of your space-time and on this projection map. If you do this, you can, well, you have this Lagrangian, you can compute the stress energy tensor, right? This is the expression that you probably are all familiar. This is nothing special of relativistic elasticity. But now that you sort of can construct these orthogonal metrics and everything else, you can sort of simplify this to this right-hand side of the expression. And now one thing is very clear to see is that if you consider the basically observers that are co-moving with particles, you see that the Lagrangian is just the energy density of the medium, because basically the term that is on the left of this last part of the equation is 0, and you only get the last part and T00, which is the energy density. And so, in fact, exactly, the Lagrangian is just the energy density. And this is also true for fluids, by the way. Up until here, nothing distinguishes an elastic medium from a fluid. So, choosing a form for the energy density actually corresponds to choosing the inelastic law or an equation of state. Now, let's do this a bit more in our physics language. So, again, we have a Lagrangian, we can construct this stress energy tensor. And in some coordinates, why there's something there in the middle, but does not matter. And so the stress energy tensor will have this form, where this sigma mu nu that is here is actually the Cauchy stress tensor, which is basically orthogonal to the world lines of the particles and to the forward velocity. So the thing that I want to mention here is that this form that I've mentioned, that the equation of state can be written in relativistic elasticity, is not very clear, and is also there's a lot of generality on how you can do it. So you need to make some simplifications, and the first simplification that you make is to consider homogeneous materials, and basically says that this will not depend on X specifically. So if you have a material, the energy density will not depend where you are in the material specifically. The other simplification that we are going to make is that the material is isotropic. And so this is a bit more complex to see right now, but just means that instead of having Hij there, it only depends on it specifically through its eigenvalues, and specifically through the principal invariants, which are a combination of the eigenvalues. Now let's just see what this actually represents physically. So the eigenvalues of this sort of this stretch that I've just mentioned, this projection of the metric in your reference space, is basically something that tells you sort of how the sizes of your fluid element are stretched when you deform the object. And equivalently, this is sort of a way to define the linear density, which are the densities along the principal directions of your material. And so, using these simplifications, you basically get a very nice form for the stress energy tensor, which is basically a diagonal stress energy tensor with this form here, where these PIs that are here are just the pressures we can compute them, and they have exactly this expression here. So the derivative of the energy density with respect to these linear densities. Now, if you remember the case of the fluids that I've mentioned in the last lecture, this is the expression that you get for fluids. So you see that there is quite a lot of similarities between the two expressions. Although in the case on the right, this n is the number density of particles, which is sort of the inverse of the volume, while here is the inverse of the length. Okay, so in the end, relativistic elasticity theory basically tells you how you can get all the pressures in your material just from the equation of state. And again, the equation of state is just this form for the energy density. So, in fact, you don't need any additional equations of state. You just need to say, what is my energy density in the material? And how does it depend on these densities? So, the formalism also allows you to compute the sound speeds. And for general types of materials, you actually have two types of waves, as you know. You have longitudinal waves. So, for example, imagine that you have, well, this axis that is here. Longitudinal waves are waves that are propagating in the same direction that they are oscillating. So, for example, if it's propagating upwards in the direction of z, it's also oscillating in that direction. And then you have transverse waves that, well, exactly the opposite. They are oscillating in one direction, but they are propagating in another. And this gives you a total of 9 types of sound speeds. And in fact, for the anisotropic stars that I mentioned before, there was no formalism to compute the sound speed. So it could well be the case that some of these solutions that I've mentioned have some of these sound speeds become much larger than 1, and these solutions are not physical. So this is a good thing that we have now that you can study, because we'll allow to understand if our solutions are causal or not. And so let's do that a bit more concretely. As I've mentioned, the stress energy tensor is diagonal. It turns out that it's exactly the same, an elastic matter tensor is exactly the same as an isotropic fluid. They are the same thing exactly. So the system of equations that you need to solve is exactly the same as the system that I've just mentioned, which are the anisotropic, Tolman, Oppenheimer, Volkov equations, which are these 3 equations that I have here. And I've just said a few minutes ago, the 2 on the left are exactly the same as the perfect fluid, and the only modification is this one here on the right. And now we just need to specify our equation of state. And our equation of state, as I've mentioned, is something that will depend on the eigenvalues of that matrix or the linear densities. Here, I'm writing in terms of 2 variables. You don't need to know exactly what they are, but they are a more convenient combination. The point is that this delta here is basically the number density of particles, so the one that appears in the expression for fluids. And this zeta that is here, well, is one of the other eigenvalues, but it turns out that is basically related to the average number density of particles. And the important point to note is that this eta function that I just described, or this n2, well, either of these n's, can be described entirely from this delta. So, in fact, once you specify delta, everything is, well, is done. Well, once you find everything is done in terms of delta, that's what I mean. And exactly, these are just the pressures, in this case of spherical symmetry. As I've mentioned, everything depends on delta. So the system is closed. You can solve all of these equations. You prescribe an equation of state. You know how to compute eta. You know how to compute the pressures. Everything is done. You are happy. You can do a solution. And so now let's go, of course, in the last question, which is how do you prescribe an equation of state? Well, we start with the simplest case here, which is sort of a polytropic. It's also a natural follow-up of last lecture. So to recall, this was the expression that we had yesterday for the polytrope. Again, this is not the expression that perhaps you are more used to see when you think about the polytrope. But again, I want to highlight, and in a very important way, that sort of the more general way to describe equation of state is to write energy density as a function of the number density of particles, or in this case, this curly row that I have here is the mass density. And this is the polytrope. And so what I just do, well, let me add a term that is quadratic in this, well, sort of deformation, which is this curly eta minus rho. And these are basically the delta and eta that I had before, but I just, well, rescaling them with some factors, because it turns out that you don't need to, if you do this sort of rescaling that I do, the reference state disappears. And this sort of makes sense because for fluids you never thought about reference state at all. So in some cases, the reference date is really not important. These are the cases where basically your material does not necessarily need to be in a perfect state. It can be whatever you want. And this is exactly what I just said. And so you can solve the TOV equations for this elastic theory and obtain some solutions. And this is sort of what I got for, in this case, these two polytropes. Here, these are, again, the mass and compactness radius diagrams for different types of this epsilon, which is sort of the strengths of the elasticity, which is sort of analogous to the strengths of the anisotropy that I had before. And there are some curious and analogous things that you can see here. For example, as you are increasing this parameter, you are increasing also the mass of your solution and also the compactness. But there's a caveat, because now we can, in fact, compute all those sound speeds that I've just mentioned. And in fact, when the sound speeds become larger than 1, I'm putting them in dashed lines there. So all the solutions that are in dashed lines have at least some sound speed that is above 1. And so as you see, if you increase elasticity too much or the density too much, your solutions will become, well, superluminal. So you need to be very careful when you do this. And this also sort of suggests that in the anisotropic studies that we have done before, there could be some of these sound speeds that you could not compute that could go above 1. And just to remark, the dot that is in the plot is the maximum mass, as you can see. And if you look specifically to the panel that is on the bottom on the left, and you look at the green curve, you see already here a solution that has a bit of solid line that goes above the photosphere, and it's on the right of the dot, so it's in the stable branch of your solution. So this is a solution that is stable as a photosphere, and it satisfies, well, at least the causal wave propagation. Okay, what are these dots? Yeah, these are just correspond to the maximum mass, but it's just to represent them in the bottom plot, because otherwise you could not see where the stable branches were. So in this case, everything on, if you look at the, well, in either plot, everything that is sort of on the right of part of the curve from the dot is the stable branch. Anything on the left is unstable branch. So there's this very tiny green region there, which is above the photosphere and in the stable branch of the solution. And so, yeah, this sort of again, sort of what I just mentioned, I just want to highlight that it's important to look very careful to the sound speeds, specifically because there's this one of the sound speed that goes, well, that goes in a steeper way is what I call here, well, is this red curve here, which is sort of the speed of longitudinal waves that propagate in tangential directions of your body. And this is one of the sound speeds that you have no idea how to do in the case of anisotropic stars. So this is why I say that it's very likely that in some of those models you can have superluminal wave propagation. Okay, it's almost finishing, I guess. How much time do I have? I still have 10 minutes. Okay, perfect. Perhaps I can finish this one. So there was another solution. Okay, let me just sort of close this chapter here. So this was a very simple example. And it already tells you that, well, you need to be careful with these sound speeds, but you can have ultra-compact objects, so objects with the photosphere that are stable and have causal wave propagation. But then you can make this question. So what, again, the question that we had last lecture, what is the most compact object that you can make that satisfies these conditions? And for that, we go back to what we had in the last lecture, which is sort of the constant sound speed equation of state. So imagine that you have an object which have all sound speeds equal to 1. You don't expect that you can have an object that's more compact than that, because if it's become more compact and more dense, probably the wave propagation will become above the speed of light. So now we want to generalize this equation that we have here for fluids, which is the equation, the affine equation of state that leads to the MIT bag models and the Christodoulou phase materials and all of those materials that were studied in the literature. And using the expressions that I had before for the sound speed, we can actually sort of reverse the problem and solve an ordinary differential equation for the energy density and try to figure out what is the form of energy density that will give you constant sound speeds. But turns out that you don't have enough freedom in your system to put all sound speeds equals to 1 or equal to constant. But you can do it for longitudinal wave speeds. And since these have also to be larger than the speed of transverse waves, it makes sense to consider these as the ones that are constant. Okay, so this is the expression that we have, and you see there that this sort of gives you an equation. Well, if you think that CL is constant and you want to find rho, you basically need to solve that system of differential equations that are there. It turns out that the solution is a bit messy, is what's here in the bottom, but the good thing is that at least there's a solution. So there's a lot of terms here that are not really important to understand. The thing that I want to highlight here is that you really have sort of a closed form solution, which is basically one line that depends on this delta and eta that I mentioned before, and two additional parameters, well, three. Gamma, which is sort of related to the sound speed of your material, with gamma equal to 2 corresponds to the speed of light. You have this parameter nu, which is the shear modulus of your material. So if you go back to your classes of continuum, well, fluid mechanics and whatever, you probably know what is this nu. And theta is an additional parameter that, well, sort of does not have an analog in those courses, but is an additional elastic parameter. So if you want to restrict to these parameters to some realistic physical conditions, you can sort of restrict the parameter space to that region that is in the middle of that plot. So these are the two parameters that you need to consider. You can only be sort of in the middle if you want to satisfy, well, physical conditions for every density that you want. But sometimes you can go a bit out of these regions if you don't care about those necessary conditions. And as you see here, there's a lot of things that go wrong if you go out. For example, imaginary sound speeds, negative densities, energy conditions that go wrong, etc., etc., etc. So you really want to stay there in a very nice closed region in the middle, which is very good, because otherwise you would have to, well, explore an infinite parameter space. And so this is sort of what we did. Well, not the infinite parameter space, explore these regions. And so these are contour plots that give you sort of the maximum compactness that a star can have for each combination of these parameters. And as you see here on the left, basically the compactness is actually very high, and it can go more or less up to 0.443. Interestingly, this limit actually is very close to Bookdahl limit. It's actually 0.44399 something, but I could not figure out if there was any connection or not. I don't think so. It's probably a coincidence, but it's a very interesting one. And on the right panel is the same thing, but I'm also considering radial stability. So I'm only considering the curves up to the maximum mass. And if you consider radial stability, actually this bound becomes much lower, 0.384. And so let me wrap up. So I want to conclude here. Actually not here. This was a a slide that I had in the last lecture about these different compactness bounds. And as you see here, we have these two fluid bounds for casual wave propagation. So this 0.364 and 0.354. And now with this work, we were able to extend these bounds to include other types of materials. So materials that are in general elastic, so very general materials, which include fluids and anything else that you can think about that's here and can be described by a sort of agglomerate of matter. And this bound becomes much larger. For example, in the case of physical admissible stars that are not considering stability, this goes up to that 0.443. And if you consider radial stability, well, does not increase that much, but still much more than we had before. And so I think it's with this slide that I'll stop here, and I'll continue next lecture with the other things. So thank you.
Thank you, Guilherme. So, any questions? No? Last chance.
Can you go back a little bit, just? So no, that one. So say again. Sorry, I missed a little bit what you said. So in the left you have, so it's regardless of the stability.
Yeah. So what I'm doing here, taking the vertical point, I'm computing the mass radius curve and the fastness curve.
Okay.
And I think the solution that has the highest compact is somewhere there.
Okay.
I don't care about the here on the right. I stop this curve at the maximum mass.
Okay, I see. So for let us say existence sake, I should be looking more into the right region, or on what you want. I see. Okay. Okay. Which still has light rings and everything. Oh. Okay, thank you.
Thank you, Caio. Any more questions? No, so let's thank the speaker again.